Hello everyone, and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry, and today I'm going to run through a few undergraduate, high school level physics questions. So here's our first one. So starting with the formula for the moment of inertia of a rod rotated about an axis through one end perpendicular to its length. So that would be something like this, where this is the axis and that's the rod of length L. Then the moment of inertia is given as ml squared over 3. And it wants us to prove that the moment of inertia about an axis perpendicular to its length but through its center. So here's a rod, and now there's the axis, where now this is at L over 2. Or at the center of mass of the rod. And it wants us to prove that it's ml squared over 12. So the easiest way to do this is to use the fact that the moment of inertia about any axis perpendicular to one about its center of mass can just be found by adding md squared, where d is the distance that we're adding, or the distance that we're translating the axis. So in this case, we're looking for the center of mass, and we have a different one. So we'd want to rearrange this. So our I about the center of mass should just be I, our given I minus md squared. And then in this case, our d is just L over 2. So plugging in the values that were given. So this would be ml squared over 3 minus m L over 2 squared, which is ml squared over 3 minus ml squared over 4. And now giving them similar denominators. So 4 ml squared over 12 minus 3 ml squared over 12. And so then that equals ml squared over 12. And so our I about our center of mass is just ml squared over 12, which is what we were asked to prove, so presumably that's the right answer. Okay, so the moment of inertia about one end, so we can use this equation. It needs to be rearranged, so that looks good. We've moved by this L over 2, so that looks good. And okay, so all that looks good to me. So solution is correct. Okay. Okay, so here I've got moment of inertia for a disk. This can, it of course depends on the axis, but I'm just going to run through a couple the more typical axes. So if we just consider an axis which goes to the center and is perpendicular to the disk, then our moment of inertia is, for a continuous object, is going to be the integral of r squared dm. And the trick is always to identify this dm And so if we consider a small area of mass at some r away and some thickness dr, we can extend this out. And so this length would be 2 pi r because it's a circle, and its thickness is dr, giving it an area, or a small unit of area, of just 2 pi r dr. Right, so this is a line segment, or we're considering, I guess, as a rectangle, so you just multiply the width times the height. Now, to get from an area to a mass, we have to use the density, or the area density anyway. So this would translate then to some small amount of mass by multiplying by the density, where for the full disk, we must have that the mass, I'm going to use capital M just to differentiate. We must have that the mass is the density times the area, which for a disk is the density times pi r squared, where r here is the full radius. Again, just to, oops, that shouldn't be an equals there. Again, I'm just going to use capital R to differentiate from the lowercase r, which I'm using for the small segments. Okay, so if that's our area segment, then now we can say that our moment of inertia is integral r squared times rho 2 pi r dr, which is rho times 2 pi integral r cubed dr from 0 to r, as we're integrating from 0 out to the full radius. And so we have 2 pi rho. The integral of a power is you just pop the power up by 1 and then divide, so it'll be r to the 4th over 4. And our limits are 0 to r. And now when r equals 0, we can see that this is going to be 0, so we just need the upper limit. So then 2 pi rho r to the 4th over 4. And so we can cancel this 2, but we can also notice that we just defined our mass as rho pi r squared. And so that's in here. So we can take out the pi, the rho, and r squared to give us m r squared over 2. And so there's our moment of inertia for an axis which passes through the center of the disk and is perpendicular to the disk. Now I'm just going to expand this by also doing for an axis which passes through the center but lies in the plane of the disk. So again, it'll be the integral of r squared dm, but now our mass segments are a little trickier. So if we wanted to identify one, it would be, and remember the r's are always perpendicular distances, so these would be our r's, and here's one such segment where it would have all the same r from the axis. So I'm just going to expand it a bit. Okay, and we're just looking at this half of the circle right now, right? So these would all be the same r's. And now it's handy to move to a theta system. So that would be theta in there. The reason I say this is because now we can define, and you'll notice that this is the radius of the circle, right? And so this side is r cos theta, and this side over here is r sine theta, and that equals our r, right? So our r value is r sine theta, and this length here is our cos theta, meaning that the entire length is 2r cos theta. So that's our little mass segment, and if it has a width of dr, then our tiny area segment this time is 2r cos theta dr. Now we want to move to a theta system, and so the easiest way to do that is going to be to just use integrals. So if r is r sine theta, then dr is r cos theta d theta. Plugging that in for our dr, then our area segment is now 2r squared cos squared theta d theta. And again, similar to above, we can now define a small amount of mass as rho 2r squared cos squared theta d theta. Now plugging in these values for our mode of inertia expression, right? So now r squared, so integral of r sine theta squared, and then our dm, which is now rho 2r squared cos squared theta d theta. And now our integration limits. So the way I defined everything is we only need to move from 0 to pi over 2, because that'll cover the whole half circle, but then that's only half of the object, so we need to double it. So it would be double 0 to pi over 2. Okay, so now collecting some of these constants out front. So I've got a rho r squared and another r squared. These are all the full radius of the circle, so that would be 4 rho r to the 4th integral 0 to pi over 2 sine squared theta cos squared theta d theta. Okay, so now for this integral, I had to look it up. So then our mode of inertia is 4 rho r to the 4th. And so the indefinite integral is 1 over 32 times 4 theta minus sine of 4 theta from 0 to pi over 2. So now plugging in our limits, 4 rho r to the 4th, 1 over 32, 4 times pi over 2 minus sine of 4 times pi over 2 minus 1 over 32 times 4 times 0 minus sine of 4 times 0. So obviously that's 0, so this whole term is 0, and that's sine of 4 pi over 2, which is the sine of 2 pi, which is 0. So pretty much everything goes to 0 except the first term. So then we've got 4 rho r to the 4th times So just moving some stuff around in here, 2 pi over 16, which is equal to pi rho r to the 4th over, so 2 times 4 is 8, 8 over 16 is 2, which means I messed something up. What did I do here? 4. So that should be 2. Oh, oops, there should be a 2. Should be a 2 here. There we go, that's what I messed up. So that should just be pi over 16. There we go, and then that should be pi, that should be over 4. Okay, there. And then our full mass is defined as rho pi r squared. So then now our mode of inertia is mr squared over 4. Alright. So that's for an axis which passes through the center of the disk and is in the plane of the disk. And this is for the mode of inertia, which lies about an axis which is perpendicular to the disk and passes through the center. And as I showed in a previous question, we can move to pretty much any other axis that's perpendicular to these ones fairly readily. Okay, so just running through the solution here. So we've got our mass, our density, our radius. So here's so this is just for the axis perpendicular to the disk, which is fine. As this question just asks moment of inertia for a disk, so it doesn't define any axis system. So I'd say this looks good. I just expanded upon it a little bit, and there's obviously other axis systems which would be possible. Okay, what is the equivalent resistance between points A and B? So I'll just draw the figure here. So we've got A. My resistances probably need a bit of work, but that's fine. I'm pretty sure it's somewhat obvious what these are. Okay, so what's the equivalent resistance between A and B? We're given that this is 3.70 ohms, 2.20 ohms, 2.00, 5.10, 4.40, 6.20. Okay, so we're going to need to use just 2 equations here. So if we have resistances in series, then our total resistance is just the sum of the resistors. Whereas if we have resistances in parallel, then 1 over the resistance, the total resistance, is the sum of 1 over those resistances. So now just to apply this, so we've got some resistances in parallel, or some resistors in parallel and some resistors in series here. And we're going to need to apply these in different orders. So if we look here, these are all in series, and they're in parallel with this guy, and then that segment's in series. So first, let's start off by that. So the total resistance there is just because it's in series, the sum, so 2.20 plus 2.00 plus 4.40, and that comes out to be 8.60 ohms. And so we can redraw the figure as something like this. So we've got, and so we've collapsed those 3 resistors into one, and so we've got this 5.10 ohms, and then this 8.60 ohms, 3.70, and 6.20. And now this segment is in parallel. So 1 over the resistance here is 1 over 5.10 plus 1 over 8.60, which is equal to 0.312, or the resistance is 3.20. And so now we have another equivalent circuit we can draw, where now we have A, I went into something. Okay, 3.70, 6.20, and 3.20. And now we just have 3 resistors in series, so our R is just 3.70 plus 3.20 plus 6.20, which comes out to be 13.1 ohms. 10, I guess, in retrospect. There we go. So 13.10 ohms. So there's our total resistance between points A and B. So treat the first segment as series, then parallel, then series, and we get 13.10. So that looks good. Okay. When will the angular momentum of a system be constant? So this is kind of another parallel that we have with linear motion. So our angular momentum is defined as I omega, at least, actually no, that seems pretty good. So L will be constant. So L is obviously going to be a constant if our omega is constant, as I is just our mode of inertia. As similar to linear motion, we can do a conservation of angular momentum. So L1 equals L2. So we can have changes in these quantities in I or omega, but omega must always be constant in either case. So what I mean by that is really alpha is d omega by dt, and so that must be 0. And so if our alpha is 0, even if, say, omega changes, so we go from one value to another value, as long as there's no long-term acceleration, angular acceleration, then our L should be constant. So another way of saying this, though, is since our torque is I alpha, again, very similar to linear motion, its L will be constant with no external torque. Right, so again, think of linear motion, and our momentum is constant with no external force. So there's There's a parallel in almost every way between angular motion and linear motion, and it kind of makes it a little easier to remember this stuff. So our L is constant as long as there's no external torque acting on the system, or no net torque acting on the system, as we need our alpha to be 0, and so our torque has to equal 0. Yeah, so then our angular momentum will change if there's a net torque on the system. So that seems pretty good. So that's just I omega. We'll get angular acceleration if there's a torque, and then the angular momentum will change. So that looks good. Okay, so for here I'll just have to draw the figure. So it's a simple understanding-based question here. So if we have a spring with a mass on it, and it's stretched to x equals a, where x equals 0 is its equilibrium position, and then there's minus a. There's a few multiple choice answers here, one of which you can't see, but it just asks, after the block is released from x equals a, will it remain at rest, move to the left until it reaches equilibrium, so that would be 0, and then stop, move until it reaches x equals minus a and then stop, or move to minus a and then continue going back and forth. So as we probably realize with spring questions, right, so this is going to go to minus a and then it's going to go back, and in fact without friction our potential energy at a is just a half Ka squared. So without friction our energy will be always constant as kinetic or potential plus kinetic, where our kinetic energy is a half mv squared, and so it'll just keep going back and forth without friction, swapping the potential energy into kinetic energy. But when it's released from A, initially it's just going to move towards minus A and then go back to the right. If you expand this, you'll see that that's actually answer D, move to minus A, then move right. Okay. As soon as the block is released and given the acceleration A, the block will move to the left until it reaches point 0, where the spring exerts a force. This will reduce this acceleration until it reaches the same magnitude minus A, but this acceleration causes the block to move to the right. Yeah. Okay. I guess it should be identified as the multiple choice answer D. But other than that, it looks good. Okay. Okay, so here we have a vertical spring. So we have a spring hanging from a rooftop and being suspended by some mass, and the length, so we're going to take 0 as this roof here that I've drawn, and the length is 0.175 meters when M1 equals 0.15 kilograms, And so I'm probably not going to draw this to scale because this is 0.775 meters, so obviously not 7 times longer. When M2 equals 1.95 kilograms. Okay. And so it wants to know what the force constant is on the spring. Okay, so first let's identify the forces in place here. So we have some mass. We're going to have our gravitational force, which is mg. And it must be being balanced by the spring force, which is minus k x minus xe squared, or not squared, sorry. Mixing it up with the potential. So just minus k x minus xe. So x would be its full stretching distance, while xe must be whatever distance it is stretched to. So then x minus xe is this distance here. Okay. But we don't need really to worry about that. And we want to keep all of our units in properly here, right? So for M1, our force is minus K. And I should have put meters there, but that's okay. So our full distance is minus 0.175 meters. And our xe, we can just leave it as minus xe and let the sign kind of take care of itself. Okay, so then that would be that force. And then we're going to minus mg. I'm going to move it to the other line just so I have some space. So minus 0.15 kilograms times our gravitational constant, so 9.8 meters per second squared. And that's going to equal 0 because the mass isn't accelerating, it's just sitting in place. Okay, so I'm going to rewrite this out a bit, or actually I'm going to write my second equation over here, right? So for the second equation, it's very similar, so it's going to be minus k minus 0.775 meters. And xe is still going to be in the same spot, so we can still use minus xe, and then minus our mg, so 1.95 kilograms times 9.8 meters per second squared is equal to 0. Okay, so now we have two equations and two unknowns. So I'm just going to rewrite those equations out. So our first one is minus, I'm going to pull out some of these minuses here. So I've got k 0.175 meters plus xe minus 0.15. Can I do that out? Or did I just leave it? I just left it, okay. 0.15 kilograms times 9.8 meters per second squared equals 0. And our second equation is k times 0.775 meters plus xe minus 1.95 kilograms times 9.8 equals 0. So those are two equations. And now we want to do something with these to get our force constant. So the more obvious thing here is then to say 2 minus 1. So take the second equation and subtract the first equation. And so then we're left with, because these xe's will cancel, we're left with k 0.775 meters minus 0.175 meters. Just collecting the like terms in k. And then minus 9.8 meters per second squared. Actually, I didn't do it that way, so I'm just going to leave it. Minus 1.95 kilograms, 9.8 meters per second squared, plus 0.15 times 9.8 meters per second squared, all equals 0. Okay, so now rearranging and solving for k. So our k is then 1.95 kilograms times 9.8 meters per second squared minus over 0.775 meters minus 0.175. And this, when we do these out, comes out to be 29.4 kilograms per second squared. And remember, a Newton is a kilogram meters per second squared. So this is really 29.4 newtons per meter. Right, so if we divide this by meters, we get kilograms per second squared, so that looks good. So this is only the first part of the question. So we still need to figure out the unloaded length of the spring. But we can already compare to the solution here, as the solution only goes up to here. And unfortunately, they used K. They used the mass as 0.195 instead of 1.95. They also have G's in here, so their spring constant comes out to be much too small. And also, yeah, I'm not really sure. So I'm not going to bother trying to figure out what went wrong in their solution. It's just wrong. But you can easily see that the mass they used is incorrect. Okay, so now I'm just going to go forward and figure out the unloaded length. So there's our spring constant. Now we can use either of our equations 1 or 2 to get the unloaded length. And so I think I used, I used both. Okay, so I'm just going to use the first equation here. So we've got, from our first equation, we've got K 0.175 meters plus XE minus 0.15 kilograms, 9.8 meters per second squared equals 0. So we can solve for, so move this piece over, divide by K, 0.15 kilograms, 9.8 meters per second squared over K. Putting in our value for K, so 29.4 kilograms per second squared. And so our XE, so our equilibrium length, is then just this value, which comes out to be 0.050 meters. So you can see the kilograms will cancel, the second squareds will cancel. Minus 0.175 meters, which is equal to 0.125 meters. Negative. And the negative's good because, as I said at the beginning, we're just going to leave the sign on xe alone and let the question figure out the sign. And so minus xe is good because our 0 is up here. So that's 0.125 meters. Right, so negative would be below the 0. If it was above the 0, then that would be an indicator that we made a mistake. And we would get the same answer regardless of which equation we used because it's the same xe. Okay, so there's our solution. The K comes out to be 29.4, and our equilibrium length is 0.125 meters. Oh, it asks for it in centimeters, so equals negative 12.5 centimeters. And I did that by multiplying by 100 centimeters per meter. Okay, so this solution is incorrect. Incorrect mass used. K is wrong. Also, question is not complete. So I'm just going to say that's just wrong. And, okay, so what's the acceleration due to gravity equation? All right, so this is, I believe, my 7th, but I don't know if I've been numbering it. Okay, so our acceleration due to gravity, I assume it means on the planet Earth, or at least that's what I'm going to do it for. So our gravitational equation is given by gmm over r squared, or at least this is usually how it's represented, where g is our gravitational constant, 6.76748 times 10 to the minus 11 meters cubed per kilograms second squared. Now, if we're going to apply this to the surface of the Earth, then we would use the radius of the Earth, which is 6.371 times 10 to the 3 meters. And our big M would be the mass of the Earth, which is just 5.972 times 10 to the 24 kilograms. And the little m doesn't matter. The reason for that is because our gravitational force is equal to our mass times our acceleration. So the little masses cancel, which means our acceleration due to gravity is just gm over r squared. And now we can plug in these terms, 6.67408 times 10 to the minus 11 per kilogram second squared. Our big M is 5.972. And our radius is 6.371 times 10 to the 3 meters. And that's squared. So now the meters, the kilogram is going to cancel. The meters will reduce this to just the meter, so we've got meters per second squared, which is an appropriate acceleration unit. And if we run this through our calculator, we'll get 9.8 meters per second squared, 196 meters per second squared, which has a little bit of error in it because we're using an average. I'm not really sure what value they normally use, so I think it usually comes out to be 9.81, so I think we're a little high, but in any case, our acceleration due to gravity is 9.8 meters per second squared. So that looks good. Okay. So just GM over R squared. Yep. Okay. So that looks good. Could be solved. And values for 9.8 meters per second squared. Okay, looks good. What is electromagnetic energy? Usually we think of this in terms of light. So our E and M energy so given a light wave, which has some wavelength and some frequency, then our energy is given by h nu, where that's Planck's constant, and that's our frequency there. But also, as well, with any wave, but in particular for light, our speed of light is the product of our frequency and our wavelength, and so we can also define our energy as hc over lambda. And these are energies per photon, right? So energy per photon. Yeah. So these expressions give us our energy per photon of an electromagnetic wave. Yeah. So, and so here we've got, as we increase frequency, we increase energy, so that that's what we expect. We're talking about electromagnetic energy only. Okay. So, in any case, that's the energy expression. And I would say this is correct. It doesn't give any kind of equation for it, but that's fine. It's just talking about how the electromagnetic spectrum tends to increase in energy from infrared towards ultraviolet and X-rays. So that, I think, is pretty good. Okay. So here we've got two mirrors, and I'm just going to draw the figure. And they make an angle theta. And then we've got our rays, which come in and bounce out and bounce around. And we're asked to show that this angle beta is equal to 180 minus 2 theta. Okay, so the way to do this is to look at these angles here, and I'm just going to call this A. And now for a reflective surface, our angle in is equal to our angle out. So that means that those are both A there. And if I call that B, then that's also B there. So that means that that whole thing is 2B and that whole thing is 2A. But the biggest thing that's going to help here is that that's a right angle, and that's a right angle. And remember that the sum of angles inside a triangle is 180. So that means that this angle here, I'm going to call it, this angle here is just 90 minus B. And this angle here is 90 minus A. And that means that theta plus 90 minus B plus 90 minus A is equal to 180. Okay? And then this angle is beta, but also this angle in here is beta, as they're similar triangles or similar angles. And so if we look at the angles in this triangle over here, so this is just looking at this triangle. So now if we look at the angles inside this one, then we've got 2A plus 2B plus beta equals 180. So we can solve this for A plus B by saying that A plus B is equal to beta, is equal to 180 minus beta over 2. And then if we look at this equation, we can solve this for A plus B by saying that minus A plus B is equal to 180 minus 180 minus theta, which is equal to just minus theta. So then A plus B is equal to theta. And so then we basically have the solution here. So theta is equal to 180 minus beta over 2 from this expression. Multiply by 2. So then 2 theta is 180 minus beta. Rearranging, beta is 180 minus 2 theta. And then there's our solution. Okay, so that looks pretty good. If we scroll down, so we can grab the angles up here. So they solve for gamma, which is this angle up here. Showed that it was 90 minus, or that this angle in here is 90 minus gamma. So they basically are moving around the triangle. So this is a slightly different method that I use, but I think it should be fine. And solve for epsilon, but then epsilon and beta are the same, and it's 180 minus 2 theta. So that looks good. Okay. And so this one is just an understanding-based question. Which is, which of the following is not one of Newton's laws of motion? So I'm just going to write out a bit the different ones, especially the ones we can't see. So there's what goes up must come down, which we can see. The second one is rate of change of momentum is force. So rate of change of momentum is dp by dt. Remember, the momentum is mv, so this is m dv by dt, which is ma, which equals our force. So that's all B's saying. So that's actually our second law. So that's definitely one of the laws. C is, in the absence of a force, an object moves with constant velocity. So so if F equals 0, then V is constant. And I believe that's Newton's first law. And D is for any force, there is an equal and opposite force. So that would be if you push on a wall, right, then you get a normal force from the wall. So for each force, there's an equal and opposite reaction force, and that would be Newton's third law. So the only one that's left, and presumably we could identify anyway, is the what goes up must come down. The other ones are the three laws. Okay. And so they identified as A, so that looks good. So solution is correct. Okay. All right. So I should have, I think, time. So I'm gonna run through this one. So we've got a rod of length L, which is at some angle theta with respect to the horizontal, and the rod's moving with a velocity v. So we're going to use our, and we're going to show that the rod, as observed by an observer, is compressed. So we're going to use our special relativity equations, so which has this form. But now we're at an angle. So rather than using this, we have to use, we actually have to use the different directions here. So it's only going to be observed to be compressed in one direction, specifically the direction that it's moving. So if that's its length, then, and that's theta, then that's L cos theta, and that's L sine theta. So that means that our x direction is going to be compressed, so our Lx is going to be our x direction, which is L cos theta, square root of 1 minus v squared over c squared. And so our total rod's length is going to be L squared is Lx squared plus Ly squared. And our y isn't going to be compressed. So this is going to be L squared cos squared theta, square root of 1 minus v squared over c squared, plus L squared sine squared theta. And that square root will no longer be there because it should be squared. And now summing the terms, or separating the terms, we have L squared cos squared theta plus sine squared theta minus an L squared cos squared theta v squared over c squared. So just separating and collecting, that equals 1. And so, and I'm going to bring out the L squared, so L squared 1 minus v squared over c squared cos squared theta. And so our length now, I guess I should have called it, in retrospect, call this LP. That way we can differentiate. So then our LP, taking the square of both sides, or the square root of both sides, is then L root 1 minus v squared over c squared cos squared theta. And so that was what we were asked to find or show. So that looks good. And then it also wants us to find the new angle and show that the angle is also being altered by the motion. And so if we look, right, our angle is Lx, Ly, and we've got a new a theta p, right? And we've got an Lx and an Ly. So Ly isn't being compressed. So we already showed that it's only x that's being compressed. So we've got our LP. This is still L sine theta. And this is now L cos theta root 1 minus v squared over c squared. And so this is our theta p. And so then our tan theta p is equal to opposite over adjacent, so L sine theta over L cos theta square root 1 minus v squared over c squared. The L's cancel. Sine theta over cos theta is just tan theta. So then tan theta p is tan theta over root 1 minus v squared over c squared. And usually that term is called gamma, so gamma tan theta, which is again what we were asked to show, that the angle now goes to a gamma tan theta. So the angle that it makes with the horizontal is also changing. It's compressing along the x direction and changing the angle that it makes. Okay, so since the rod makes an angle from the horizontal, length contraction in both axes, so no, it'll just be in the x, but that's probably just a mistake. So the compression along the y is nothing, so it's not being compressed at all, so that's good. And you get this, and then for the angle, it's the old y divided by the new x, and so gamma is this term, so then tan theta p is gamma tan theta. So that looks good. So that's good. Solution is correct. Oh my god. All right, there we go. All right, so that looks good, and that's gonna be it for me today, actually. So I hope you enjoyed this. If you did, please subscribe to OneClass. If you want to leave questions, you should be able to follow links below the videos to submit questions. This has been Jeff Krause for OneClass.